that can work. That can work. All right. We do it that way then. So I'm giving out problems next week and then just work them and submit them. What else? What else? Oh, I don't know. Most of the people them work.
Yes, sir.
So it wouldn't be possible then for to move the class earlier.
Probably not.
Because at them time, the rain season now. Because right now it's overcast and all of them things now. So if it start rain and start thunder, we have to go terminate the class. So I don't know if there's a time when we could have moved it to earlier in the day. I'm pretty much flexible.
I work, but earlier wouldn't affect me. I work with it just the same. Earlier would have good for me because right now it's overcast, so I'm there and look away.
Because you're there at Ochi, right?
No man, me go watch me and me wait back to Mobile now and Mobile me there.
Mobile there.
Me driving back to Mobile now and overcast heading back down there, it look real dark.
I see me look up here in Amandable, so.
Yeah, we don't know yet.
So no can just do a survey for me.
We can discuss that, sir.
Yeah, we can discuss it and see how it go.
Yeah. But anytime earlier, anytime after 8, because I don't wake up till 8.
So 8.
Say from 9, if we could have get it all from 9 to 11, that would have better.
I see what the man wants to say, sir.
Alright. So I'm going to roll down now, right? Still 12 or more people join.
20.
20, alright. So I'm going to start now. Alright. Again, may I ask a question? Anyone have any question based on the notes when I send out?
Number 5.
Number 5. Okay, well.
I don't see how them get a Y component because when we try the sine 0, we get 0. When we try the sine pi, we get 0. So I don't see how they get a Y component.
Let me go to that note sheet there and see. Oh shit! Wrong thing.
Backside, I will go up on the screen. I'm not saying anything.
Yeah, here you are, cuss though.
So if we get cut off and reach our office, me join back because I'm on phone, me there on a drive.
So you said number 5. Or which one?
Number 5.
Let me see me find number 5.
On my screen alone, that thing you show up on? I'm not saying anything.
No, you not put up nothing yet.
Oh, because I wonder what I go on.
Yeah, you're supposed to see something now. Number 5, the one where say find the distance between A dot and B dot.
Good afternoon, Junior. What is your name?
Brian?
Sir, not up on the screen, sir.
Where are you calling from, Miss Barnett?
Not a thing up on the screen.
What do you mean, man? Hold on. Oh, shit.
Yeah, of course, sir.
And then I can't make on one because we don't have a customer. Hold on, man.
Boy.
Sir, which medium I use and send out these notes? Dr. what?
Yeah?
Sir, which
Ask,
medium I use and send out notes them?
ask Dre. I send it to Dre. Dre send it to him.
You did post in our WhatsApp group.
Oh, me in a WhatsApp group there, you know.
You can't blame me for that, but you're supposed to in there.
I never know what's a group I make, sir. But no.
So,
All right, drop your number in our chat on the admin audio.
Alright.
you see it now?
Yes, sir.
All right. This one I talk, Brian. Now, Brian, I asked about
No,
question.
Devon.
Devon
Devon.
asked about Devon.
Yes. Yes.
This one?
Yes,
Find
number
it.
5, yes.
Find the distance between A1 pi by 4 0.
Yes.
All right. So you say you have a problem with now?
When I do sine 0, I got 0.
Well, everybody get what do sine 0?
I don't know that, so I'm asking.
Then you don't know say sine 0 or 0.
Yeah, that's why I'm saying I don't see how they get a y component. Because sine pi over 4 times 0 will give you 0.
Sine pi over 4 cos 0.
Nah, man, that is the x component, but for the y component.
I mistake that, man. It's supposed to be AZ. I mistake that. Can't say it's a mistake.
But the next, that's why I'm saying the next one, when you do sine pi, you get 0 just the same.
No, this says, all right. You mean the y component would be sine pi over 4, which would be what? Sine pi by 4 is what? 1?
A root 2 over 2.
Root 2 over 2, 0.7, right?
Yeah.
Sine 0, which is 0, right?
Yeah.
So this should have been AZ.
Yeah, right. We get that as AZ.
So
But when you go down on it, but what I'm saying in the answer, they have a y component. I don't see how they get a y component. Because when you go to sine pi is 0, just the same. You follow what I say?
You lost me there, so. May I follow
All right,
this?
when you go to B,
Mm-hmm.
when you go to B, sine
Right.
pi is 0.
But you don't have no sine pi there. You have sine,
No,
the
for the
y.
y component, yes.
So you have sine 3 pi over 4. Sine pi, right?
Yeah,
So sine pi is 0.
right.
So they shouldn't have a
Y component,
y. It should have a AZ.
right.
So this should be a AZ.
Yes. But when you go down to the answer now, they have a y component.
And if they make a mistake up there, so then I'm going to carry that one. So this should be, it should come back down here as a AZ. This shouldn't be in it.
Right, because when I did mine, that's what I got. I got an x component and a z.
Yeah, so this shouldn't be in it. So there's
Okay.
that error here.
Okay.
All right?
All right, fine. Good then.
Yeah, all right, cool.
All right.
So go back now to where we there now. All right. So remember, right? What we said now was that we're going the exercise of finding the electric field, that we go through those complex integral. And we said that the whole idea to start there is to get you grounded and having an understanding as to, or an appreciation as to what you're doing. So it's like what we did earlier, where when we did a simple differentiation from first principle, we get to understand what differentiation means, and then we come up with some laws, like the product rule, the quotient rule, as to if you see a function in a certain form, you apply this rule and do the differentiation or the integration. So you start from first principle, where you get the appreciation of what you're doing when you said differentiate or integrate, and then you apply the rules to make it simpler. Likewise, we said, well, in electromagnetics, we started from first principle, where we go through the complex, the vector calculus and the complex integrals. And once we get an appreciation of what we're doing, we now apply rules to make the whole exercise simpler. I believe that the exact words I use is that we're going to do the same thing over and over, using some rules and making the problems simpler and simpler. In other words, if you believe that you can sit an exam and not knowing how to apply, if you know how to apply the rules, it can take you 3 or 5 minutes. If you don't, one question take you 5 hours. So the first rule we want to, our law we want to look at, is God's law. So if you read along here, application of God's law is in fact alternative statement to Coulomb's law. God's law can be used to find E or D for symmetric charge distribution, such as point charge, infinite line charge, infinite sheet charge, spherical distribution of charge. These are all that we went through with our vector calculus. The Gauss law is also used to find the charge enclosed or the flux passing through a closed surface. Note that whether the charge distribution is symmetrical or not, Gauss' law holds for any closed surface, but can be easily applied to symmetrical distribution. But the Gauss' law cannot be used for field E or D if the charge distribution is not symmetrical. So, let's go back here. Okay, let me go on a little further. So, what is E again?
Electric field intensity.
And what is D?
Distance.
No, man. Electric flux density. So, these everywhere either normal or tangential to the surface. So, if you have a charge, just picture in your mind you have a charge and you enclose that charge with any shape surface. So you have a point charge and you draw a circle around the point charge, right? The electric flux is the electric field passing through the surface. So then, you have a point charge and it's radiating electric field, right? You have a point charge here, you put a circle around it, and it's radiating electric field, E field going out. The electric field going through the surface is the electric flux. Wherever you choose your reference from, anywhere you would have a field line going through the surface, you could resolve it into a normal component and a tangential component. You agree with that? Do you agree with that?
Sir, the tangential component, the x component.
So, say you have a field going through the surface, right? At whatever angle it's going through, based on your reference coordinates, you can resolve it into it's like again like Pythagoras. You have the hypotenuse, right? And you can resolve that into what they call it opposite and the opposite and what?
The adjacent.
The adjacent, right? So it's gonna be either tangential or normal. So I'm saying whatever angle it's making to the surface, you can resolve it into the normal and the tangential. It's basically saying the opposite and the adjacent. Because you would have your field line, which would be the hypotenuse. And why is that important? One would either be 90 or one would be 0. Right? So D is either normal or tangential to the closed surface. Right? Why is that important? Once you resolve it, if you take the dot product of D and the surface, it's either going to be D times ds or 0. Because it's going to be either sine 0 or sine 90. Confused enough?
You mean cos 0 or cos 90?
Cos 0 or cos 90. Okay? So it's gonna either, if you resolve it into the tangential and the normal, d dot ds is either gonna be 0 or it's gonna be 90. So
It'll be 0 or 1.
right, either 0 or 1. So it's either we're gonna be cos 0 or cos 90. And cos 0 is 1, cos 90 is 0. So let's go over some of the same charge distribution that we went over last week Tuesday, starting with the point charge. So
We have trouble.
so now we have a point charge at the origin. We have what we call a Gaussian surface. Consider a differential surface ds, which is here. The normal to the surface would be going straight out, right? Which would be AR. Agree? We remember, you have a point charge here. So you're going to have field lines going all out. But we are going to look at this differential surface, ds. For this field line that's going out, the normal would be AR. That is going straight out, right? Okay. So,
So that line it would be like if you're looking into P, it coming straight into your eye.
exactamundo.
Okay. I'm confused enough.
Yeah, because that's the reason why I said that AR is normal. Normal to the
Consider a football one. And you consider any sphere. And you have a point charge in the center of the sphere. That's at the origin right here, right? So you have radiation coming out. Yeah? So where this come out now, here, it would be normal to this point, right? It would be normal to this differential surface. It's coming straight out at 90 degrees to that differential surface. I like when I'm silent, you know, brother.
Yeah, man, we're radio.
Mm. No. We went through how we would get that differential surface ds to be equal to r squared sine theta d theta d phi. Sure, so we went through that. So that is your differential surface. All right? So the differential surface vector is ds a normal. A normal is again ar. All right? Now, d, remember, you know, or did we do that? Did we say, yeah, man, we did this. Did we do D last time? Are we jumping too far? D is Q over 4 pi R square. All right. We did E, right?
Yeah.
E is Q over 4 pi epsilon R square AR.
Yeah.
Right? D is epsilon E. So D is Q over 4 pi R square AR. Which for R equal A is 4 pi over A square AR. Now, this is your ds. D dot ds is this dot d. Right? D is this, ds is that. Theta is 0 because d is in the same direction as ds. So d dot ds is q over 4 pi a square times a square sine this, which is just this, times this, which is equal to this. Now, when you do the dot product here, it comes to this. So your flux, stay confused a minute, just follow me. Remember when we did the old way, we use this, right? And we get this, which is Q. So, what we are trying to prove is if you enclose a charge, if you have a closed surface, and if you have a charge here and you enclose that charge, the total flux crossing this surface is equal to the charge enclosed. So we went through that rigmarole to say that the charge enclosed is this. The flux crossing the surface is this, which is equal to the charge enclosed, which is Q. I think I'm gonna get it, but I say,
I follow you still.
all right. So, what Gauss law state again? The total flux crossing the Gaussian surface is equal to the charge enclosed. Here where we are going with this now, Paddy. We are saying now that if we want to find electric field, right? Instead of going through all those integration to find the total charge and then whatever, we can just draw a Gaussian surface around the charge, whatever the charge is, and find the total flux crossing the Gaussian surface. And that would give you the total charge enclosed. All right.
Can you repeat that again, sir?
Remember, like when we working with Coulomb's law, right? And we want to find an electric field somewhere. The first thing we have to do is to calculate the total charge, whether it's sheet charge, volume charge, point charge, whatever. And then, only then, we can find electric field when we know the total charge. And we have to go through a series of resolution where we are finding tangential and normal component and so on and so forth. Right? Jay, I think you have to start back. Jay not there.
Yes,
Hello?
sir. I'll restart it.
Restart it then.
You having rain weather, sir?
Huh?
You having rain weather?
You just a start now, brother.
I beat it, man.
Pure rain, come like a storm there.
Eh. You guys back with me?
Yes, sir.
Okay. All right. No. Where was I now?
Start record.
Eh? All of that rigmarole is to say this. Is to say that the flux crossing the surface is equal to the charge enclosed by the surface. So all that we have gone through so far is just a proof of that. You can go over it and try to get that or to appreciate that a little more. But we're gonna use that law now to solve some of the problems that we solved last week. So we're gonna use, all right, we didn't do D, but D is just epsilon E. So we're gonna use Gauss' law now to solve those problems. Q, so you have, follow me now. Say you want to find a total charge, whatever the charge is, and you put a surface around that charge. The flux crossing the surface times the surface, which is what all this is. So that would be the total flux. You have your flux density. So your flux density would be say x coulomb per meter square. That multiplied by the entire surface would equal to the charge enclosed. All right. We already established that, say we have a point charge at the center of the sphere. The normal flux would be radiating radially. So AR would be the normal flux. Look at me now. Wherever the flux or the flux line hit the surface, we resolve it into a tangential component and a normal component, right? The tangential component is not crossing the surface. Only the normal component crossing. Oh Lord. Which is AR. So now, for the sphere, your differential surface is this, what we went through earlier. And d dot ds is that. So the integral of d dot ds is that, which is equal to the charge enclosed. Q, which all it amounts to is this. So Q equal the flux going across the surface, which is this. So Q equal that. So your flux is Q over this, and your E, you just divide by your electric field, you just divide by epsilon to give you this. So try and recall the whole lot of rigmarole that we went through when we started the other way. Using Coulomb's law last week. All we need here now is your ds, and you integrate it over the entire surface. So d dot ds is this, and q equal this. So you can find d, from which you can find e. Isn't that easier than what we did last week?
Yes, sir.
All right. Just pull up in your mind now how we find the electric, how we found the electric field for an infinite line charge last week. Look at this now. We create a Gaussian surface around the line charge. Right? So this is your line charge, rho L, and you would say X coulomb per meter for your line charge. And it's going from minus infinity to infinity. Right? You have to be smart and choose your surface. You choose your surface to be symmetrical to whatever charge you have. So you wouldn't have a surface, you wouldn't have a line charge, and then you choose a surface. It would work out still, you know, but you'd choose a surface which is symmetrical, right? Now, this is your field coming through your surface, right? So, if this differential length here is giving you a field like this, you can resolve it into this way at right angle to the surface. All right, look at this now. This is coming here. So you resolve it at right angle to the surface or tangential to the surface. So the one that's crossing normal to the surface would be AR, right? AZ, which would be here, not crossing tangent, not crossing the surface. So now, the integral over the surface of d dot ds. What is your surface? The surface go around here, the surface up here, the surface down here. So d dot ds side would be this, top and bottom. So q equal the integral over the surface of d dot ds. This, right? Like we said, the AR is the only radial component. Right? So what is your surface here? What is this surface? Surface would be RD phi dz. RD phi, which is your swing, dz, your surface. So d dot ds is this, right? D dot ds gives you this. Now, d dot ds for the top and the bottom is 0.
Sir, one thing that's what are the R I mean again? Like the ER, the subscript R. The subscript R, what is the meaning of it again?
The unit vector are in the r direction.
Okay.
Right? So, look how this work out sweet now. D dot ds for the top and the bottom is 0. You see why? Tell me why.
Gotta run in parallel with the line charge.
Perpendicular.
It running perpendicular to the flux. Because the flux are go so, no so?
Oh, to the flux. Okay.
So D dot ds cosine of 90, no, 0. No.
Sine, I mean.
Eh? Cosine of 90 is 0, right?
No, sir.
Yeah, man. Cosine of 90 is 0.
The flux are go where, sir? Which direction the flux are go?
Your flux going this way, radially out. Remember now, you resolve this little differential length, right? It's going to have radiation all about, right? But you resolve it into at right angle and parallel, right?
Right angle parallel to Z.
Yes. So parallel would be what? No. Yeah. So cos of this that's going through the surface
0.
is 0. So at the bottom and the top, that would work out to 0. So you're only left with the sides. So d dot ds and the s for the side would be r d phi dz integral. All right? Which is 2 pi r times L. This whole integral would be 2 pi r times L. Around, and along the length. So you have, oh Lord, Emmanuel! Give me a minute, I'm gonna plug out them TV, I feel, man. All right, guys, I'm back. So, where were we again? So Q is equal to this, which work out to this. So your flux, you just do the cross multiplication, and your E is your flux over this. So if you remember, when we did it from the other way, this is the same answer we got. But by applying God's law, it is much, much easier. So, similarly, if you do any of the other charge, for example, a volume charge or a sheet charge, is just as straightforward applying Gauss's law. Okay. Let's see something here. Get them confused here. All right. I remember at some point I told you that the entire electrical engineering curriculum is constructed on electromagnetics. Now, there are 4 equations that makes up the entire the entire course. Those equations are really just mathematical expression put together by a fellow by the name of Maxwell. Maxwell, 4 equations. We're going to take a look at the first equation within the concept of God's law. Now, I'm sure that we looked at what divergence was, right? Yeah, we did that. So divergence of a vector is given by partial with respect to x of, say your vector is dx ax plus dy ay plus dz az. So vector d is dx, is the partial of dx with respect to x, or the divergence of d is the partial of dx with respect to x plus the partial of dy with respect to y plus the partial of dz with respect to z. Now, we know that Q is the integral over the Gaussian surface of d dot ds. So, if our Gaussian surface form a volume V, your Q per unit volume would be this expression over whatever your unit volume is. According to limits, as your volume goes to 0, if you work out this expression, just as how we work out this simple expression when we did the differentiation of x squared. As your volume goes to 0, your charge per unit volume approach some finite value we call rho v. So rho v is the limit as your volume approach 0. So Maxwell equation says the divergence of D is equal to rho V. Divergence is the limit as your volume goes to zero. Or your differential volume goes to zero. This volume charge density around a point, the equation 6, which is this, is called Maxwell's first equation applied to electrostatics. This is also called the point of Gaussian law or Gaussian law in differential form. So del dot D is rho V. Here is where I'm going with this stuff. If you have a flux density and you want to find your charge, del dot D equal rho V, which would be your unit of volume charge. Del dot D equal rho V. You must have question on that because that I don't think I'm clear on that. You there, guys?
Yes, sir.
Yeah, man, right here. We look at it. We look at it.
By the rain I fall, man, I don't know if you not hear me good. Go on, because it like it don't really start yet, so.
So, sir,
Hmm?
the most important thing we need to take from this is that
Speak up a little for me because I can't hardly hear because of the rain.
I'm saying the important that we need to take from this is equation number 6. So,
Right.
that's the first equation. But do we need to know how we come about it or we arrive at it?
I think it's quite important to know, you know, because you will understand how they come by the equation number 6.
Okay.
So another one which we have to do before we can really move on is what they call the Passans and the Laplace equation. Now, we talk about flux density and we talk about electric field intensity, right? Now, in your networks, you talk about voltage or potential difference, and you talk about Kirchhoff's voltage and current law. This is the relationship now. You have an electric flux. You apply Maxwell equation, you get del dot E equal rho V. D is the electric flux density. D is epsilon E, which, so then, del dot D would be del dot epsilon E equal rho V. Okay. E is minus del V. V is voltage. Substitute this into this. So del dot this equal rho v. Right? So to simplify this, you'll get to this. This is known as a Poisson equation. In other words, if you know your volume charge density, rho v, you can find the voltage of the system. And if you don't have any charge, that means rho v equals 0. The equation reduced to this. It's called the Laplace equation. All right. Jay, how many people you have there now? Can we find out if we can start early on Thursday? Because I don't like how this thing is going.
28.
28. Can you do the survey now and find out if we, even if we can start, say, anytime earlier, say 12?
Good to go.
Yes, sir. Come on, sir.
All right.
Green.
Huh?
Yeah, man, sir.
All right. So just post it in the group that we're gonna start earlier because we can't deal with this lightly, you know.
Sorry, I could make Miss Donkey send out like a notice to for who who don't see it as well.
All right. Yeah, I'm going to call her now and tell her to send out. I just want to make sure you don't have no one have any conflict with any other class.
Sir,
Okay.
what time you recommending?
Huh?
What time you want to start?
Like I say, it can work anytime after 9 for me, but it totally depends on you guys. Because it looked like about 2 o'clock the rain start fall. So we want to say 10 then? Huh?
Let's start delivering everybody.
12 would have alright, cause
All right, so we start at 12 on Thursday.
yeah.
All right.
Okay, sir.
All right, cool. Sorry about that.
Yes, sir.
Done, sir. Done, sir.
Yeah, I got him gone. You know what I'm saying? Yeah, I got him gone. I want to say the weather and the rain and something. That's why I want to start the level Thursday to catch up by the time.